Hi, today we're going to start the first class on aerodynamics. Aerodynamics is an introductory course mainly for undergraduate students in their junior level. The purpose of this course is to tell you how aerodynamics especially affects not so much cars and the other applications, but airplanes. So before we start moving on, I want you to think about an airplane, okay? But that's what we're going to talk about. In this case, I work for Lockheed, so this is a model aircraft at Lockheed. And I want to think what each person does. First of all, I am a structural engineer, aerospace structural engineer. So I am interested to make sure designing these parts to make sure they're safe, they don't break. I want to make sure this is as safe and strong as possible. Now, the aerodynamic system, on the other hand, that's this course, the aerodynamics. It makes sure that studies how the flow moves around the aircraft. Aerodynamics is what shapes the aircraft. The shape, how this aircraft looks like, will depend on the aerodynamic study. And that comes from typically in the old days, we used to use wind tunnel testing. Nowadays, there's some wind tunnel testing, some testing done, but mainly we heavily rely on CFD. CFD stands for Computational Fluid Dynamics. It's basically computer modeling of how the air flows. And with that flow, we can determine what the shape should look like. Then you also have the propulsion guys, right? In this case, the propulsion system is here, what's going to produce enough thrust so this can move. Now, it's very interesting how this really works in airplanes because we typically think in the car, right? Your car is pushing this way and your car is moving that way. Well, airplanes work very differently. If you know the Newton's third law, for every action, there's a reaction, right? So that's what the airplanes actually move. So I want you to think about this is actually pushing this way, but because of action reaction, the thrust is coming here and my airplane moves in this direction. Okay, so those are the propulsion guys. They want to make this, they want to optimize this part. And then you got the control folks. The controls are the ones that make sure that this is stable. It's very interesting to see how the airplane, when it first comes out of the hangar, it can be all shaky and wobbly, and then they tweak and then what you see on the movies and your videos is basically a very nice smooth aircraft, but that's because they got a lot of controls working on that constantly. So it's a very interesting because if I want, in a structural standpoint of view, I would like to make this as block, as heavy as possible. Aerodynamicists want to make it as light as possible, want to make it like a feather. So it's a compromise. Okay, this is the result of a major compromise of all the group of people that we are working together. Okay, so this course is not going to necessarily teach you how the airplane will be strong. Actually, we will not even teach you how to shape the airplane. We would learn how to study what will shape the airplane that you can do um, in a follow-up course. Okay, so I want you to think about first of all, let's start with just a simple definition of what airplanes are. But aerodynamics is. Aerodynamics is nothing else than the study of the air that moves around a object. It can be many objects. Okay, it can be air around any solid object. Can be this object. This object can be rigid. When I say rigid, that this does not deform. Okay, this remains solid. But we know that's not true because everything that we do is elastic. So we know that the wings are going to deform. So in that case, we also study what the flow looks like around the elastic body. Okay. So aerodynamics is what explains how the airplane flies. Those are major rules that actually define and helps me to make sure my airplane is flying. So there are many, many different applications, right? You can see the application from a rocket to cars to even kites, those are very the simplest kind. So if you're into cars, right, designing cars, they spend huge amount of time studying what the aerodynamic flow looks like to make sure that they make the most optimal car for the application that you can think of. You also have, obviously, that's the purpose of this course. You can have a transport aircraft or you can have a military aircraft. And you can see that we study what the flow looks like around that. What we want to avoid is all this curly stuff. We're going to talk about that in the course. Okay, we want the flow to be as smooth as possible. That's what we do in aerodynamics. The smoother the surface, the more performance we get, the more lift we get. We will talk about that in just in a few minutes. And we also have bicycles. You might think, well, this is just a simple bicycle. Well, they got lots of fluid, CFD, computational fluid dynamics analysis done on a bicycle before you get a bicycle in your home. They want to make sure that the flow around this is as smooth as possible. So even the bicycles go through that. So this course will be very practical for many different applications. Now, some of the things that NASA program has, and they got 4 different categories. One is hypersonic. Hypersonic is nothing else than higher than Mach 5. Mach is the speed, the speed of the aircraft divided by the speed of sound. So let me write that down, and we're going to talk about this throughout the course, anyways. But when I say Mach, Mach is letter M is V over A, and this is nothing else than speed of sound. Okay, and so when you do hypersonics, you also have to make sure when you go to Mach 5, Mach 6, Mach 20, then the aerodynamics around the airspace, around the aircraft is completely different than when you're working in a supersonic or you're working a subsonic. So this is one case of problems that NASA especially is very interested. Another set of problems is the subsonic. And by the way, here in this category, all the aircraft that leaves the Earth that goes to space, those rockets are supersonic, hypersonic. Military and acrobatic aircraft are also hypersonic. Then also you have supersonic. Supersonic are the ones that basically they are bigger than 1, well, typically 0.9, and they're less than, let's say, 2 or 3. Those are supersonic. And you can see some applications for this are given here. I worked on X-59 I started my career as the empennage stress lead for X-59. You can search the program. It's a low boom program from NASA, and that's a supersonic aircraft. So we don't go Mach 2, 3, 4. We stay below Mach 2 typically, and that type of aircraft mainly is for transport aircraft, and they're actually studying that. So another projects they have is subsonic fixed wings. So subsonic, you're talking about typically Mach less than 0.9. That's considered subsonic. Your transport aircraft fly at Mach 0.8, 0.75, in many cases 0.85. So this technology is also there. And what we want to do here is we want to have fixed wings and make sure this is optimum as well. Another projects that NASA typically has, especially NASA, is the rotary wing. So the rotary wing, you can see how the aerodynamics is also being studied here. In a rotary case, like helicopters, that's also You got helicopters for subsonic, and also it can be as fast as you want. And there are lots of studies done on that. So that's basically, in a nutshell, some of the programs that NASA has, and they have direct application aerodynamics. You cannot help it when you talk about aircraft, you talk about airplanes, you cannot help it, then you cannot deassociate the aircraft from the aerodynamics. It just does not make sense. It's just they're all bound together. If you have airplanes, you're going to have aerodynamics because there's no other way that a plane will fly. Okay. Um, so let's move on. So before we move on, let's take one step back and define what is air, because obviously our airplanes fly in air. So what is air? So air, first of all, a fluid is nothing else than a gas or a liquid. So what you can immediately know that many of the concepts in fluid dynamics will be applied here. Okay. All the concepts in fluid dynamics I applied in this course. Why? Because that's where the word CFD comes from, right? Computational fluid dynamics. Why? Because this is many of these methods go back to the 1800s when they were developed, and especially knowing that air is in essence is a fluid because it's considered a gas. It's a special case of fluid. Okay, so if you're going to study hydrodynamic, if you're talking dynamics of a liquid, that's what we call hydrodynamics. Gas dynamics is nothing. I want to talk about gas. So when we talk about air, we talk about air dynamics. Okay, so in many cases, they actually exchange one from the other. It's hard to separate in many cases. In such a case, you can have a case of hydrogas aero. Okay, so that could be another possibility. And just to kind of work through some of the stuff that you probably know already, when we work with gases, we can know that we can see that the particles are all separated. They can expand, and when they are liquid, they can still expand, but they are more tied together. In a solid, they're all bundled up together. You may have voids, but they are microscopically small that you cannot see them. So in a solid, you can think about a solid that holds a solid. So think about a solid. A solid has a shape. So you're seeing it right here. You see? How do you know this is an airplane? It looks like one, right? Because it's a solid. Now, if I talk about liquid, so when we're talking about liquid, think about this particular case. You have a water bottle and has liquid that takes the shape. Now, liquid, you can see it, but can take a different shape as I pour something else. So it takes the shape of my container. So the other case is a gas. Gas basically expands and takes all the space of, or takes the shape of my container, of the volume, expands. There's no limits to the gas itself. That's the case of the air. The air doesn't necessarily have any, it takes all the space that you can possibly have. Okay, so with that said and done, let's define a few things. So if I take a solid and I apply a load to it, let's consider this case. If I take this solid, okay, and I apply load to it, okay, this is going to make this deform. It's going to have a deformation. It's going to bend. That's what we call a deformation. If I don't apply anything, there's nothing. I apply it and it deforms. Now, in the air itself, if I apply a load, because there's friction here, and I apply this air moving across this, there will be some load applied, the shear load especially. And if you think about here in solid, if I'm applying a load, that's going to deform. but in air, we talk about rate changes. So here in solid is the tangential force is proportional to the deformation. However, the shear stress in a fluid will be proportional to the rate change of deformation, rate change, not the deformation itself. Okay, to better understand this, let me change my marker. So what I mean is, if I'm applying a load, as we know, this is directly proportional to my deformation, okay? Here, basically we are saying, if I apply my shear is going to be my viscosity times rate change of my deformation. So we talk about rate changes, whereas here this is completely proportional to the deformation itself. Okay, that's one of the major differences that you have between solids and fluids. But we talk more about this in the classes ahead. The last topic I want to say before we move on today, the forces on airplane, we got 4 forces in the airplane. One is lift, we got drag, and we got weight. So I want you to consider again this particular case. This is flying, and because I have a fluid flow, I have airflow coming here, you have a smaller airflow pressure here, okay? You have a smaller pressure here and a larger pressure there, and my delta pressure is positive, then you have a lift, positive lift. If my pressure at top was higher than at the bottom, then we call negative lift. That means your airplane is going down. So the lift is important. So the faster it's going, the more lift it is. But I can also go slow and change the shape of my aircraft or my wing to make sure my lift goes up or my goes down. I can move my angle of attack. My angle of attack would create a higher surface area here, right? As you can see, this is moving. So if this is the air, look at this. This is air and it's hitting the wings, right? So you can expect is having a large area. It's coming here, then here you have air going at the top, at the bottom. You see, it's at top and at the bottom. Air goes at the top and at the bottom. So if it's higher, that's where it goes up. But in the perfect world, this is, you got this and we just move on because you got a thrust. However, just because I want you to think about this, everything has a resistance. The air acts like a spring at the same time. So as this is moving in the air is also trying to hold my aircraft. That's called drag. And that drag is also generated because the same airflow, but it's going to create vortices. It's going to create turbulence around on the surface and around the aircraft that slows down my aircraft, which we don't like. So also you have, so this is moving forward because you also have a thrust, right? So this thrust is the amount of thrust produced by your engine. Sometimes the engines are on your wings. Sometimes you have them here at the end. So these are the 3 types of loads that typically your aircrafts have. So in the case of lift, this is a positive delta pressure. It's a delta pressure. If it's positive, then is the lift. If the lift is positive, your airplane goes up. If the lift is negative, it goes down. And this is the weight of the aircraft, basically. So in essence, what we want to do is, if my thrust is bigger than D, you can immediately see that this is moving in this direction. Okay, you might say, Professor, but why is thrust given here when the engine gives thrust over here? I just told you, I explained that because of Newton's 3rd law. My thrust is going here, but because action reaction, my airplane is moving there. So we never say my thrust is going in this direction. The thrust is moving in the direction where my airplane is moving. It's opposite from cars. Okay, so typically when my airplane is landing, you're going to see that my thrust is way smaller than D. That's why they got the slat and the flaps that go up, and you hear this huge amount of noise that slows down the aircraft. In the case of space shuttles, when they come on Earth, many times they use parachutes. That's basically to increase the amount of drag, and they're coming actually at zero thrust. So in this particular course, what we will be interested, the design of thrust is more a propulsional course. Take a course in propulsion. If you want to, you're interested to know what is the optimum L over D, because we know for a fact this can never be zero, and we can know this can never be infinite. But there's an optimum value for this, okay? And this is taught in a course on uh, aircraft performance, but that's beyond the scope of this particular course. So basically, this leaves us, what we're going to learn is how does the fluid flow, how we're going to work with L, we're going to work with D, how those components are actually modeled in the aircraft throughout the course. So this basically wraps up this concludes our class on introduction.